Hello, everyone. Welcome to this free webinar presented by WePast. I'm your moderator, Christina Ruiz. During this webinar, feel free to use the chat to ask your questions and discuss the topic. We will take time after the presentation during the Q&A to answer these. Throughout the webinar, we will stop the presentation to review. Look for the multiple choice review questions, which you will be able to answer in the polls section. Please go ahead and respond to these questions as they come up. You will have less than a minute to answer each one. This and other recorded webinars are available to WePast subscribers 24 hours a day, 7 days a week. Be sure to register through wepast.com to become a subscriber. Today's topic is on TG-51, Details, Assumptions, and Common Pitfalls, presented by Dr. Stephen Cry, Associate Professor of Radiation Physics at the MD Anderson Cancer Center. He also serves as the Associate Director of the Imaging and Radiation Oncology Core in Houston and is the Director of the Accredited Dosimetry Calibration Laboratory. I'll turn it over to you, Dr. Cry.
Thank you, Christina. So I wanted to talk today about TG-51, and I titled the talk something other than Mad Ramblings on TG-51 because that seemed a little too weird. But I wanted to not talk about TG-51 as a protocol and the process because it's a fairly clear recipe in terms of what measurements you take. Instead, I wanted to talk more about what are the underlying assumptions, what are the underlying thoughts that go into this, some of the details that aren't really discussed in the protocol. And then I wanted to tie this into, of course, to where things go wrong and what mistakes have been made with the goal of avoiding those mistakes in the future. So here's the protocol, and dose is given by NDW, which is the calibration coefficient, MRaw, KQ, Pion, P temperature and pressure, P electrometer, P polarity. In the TG-51 addendum, there's also a P leakage, which is basically a background signal that you can subtract off. PRP for radial profile if you have a non-flat profile. Those are relevant, not particularly interesting. I don't actually plan on talking about those in this talk. And then you divide by the PDD at 10 is a standard step involved in that as well. And this is the full process. Instead, I'm not going to go through the process in detail, but we can think about it. And we'll do that just by asking a simple question here. Because this is the way I like to think of TG-51 when I'm going to do it. How many dosimetry measurements, locations, I'm not talking about repeat measurements, but how many measurements, how many different locations do we need to make a dosimetric measurement at to do TG-51 as a minimum? And I'll open up that question.
Okay, great. Thank you. So the first question is up in the polls section. You can go ahead and open that up and respond to this first question. And also after you respond to the question, I just want to let everyone know that if you have any questions for Dr. Cry throughout the webinar coming up, please be sure to ask those in the chat section so that we can review those later on. All right, I think a lot of people have weighed in, and it looks like some folks are definitely getting the right answer here. I think we can go ahead and review the
All right,
answer.
Moving on then. The answer is 5. This is, again, how I think about it. You need to take your actual measurement at 10 centimeters depth. This is the reading used for the calibration. You need to repeat that with the opposite polarity to get P polarity. You need to do that at half bias to get Pion. So it's 3 measurements. And then you just need to measure KQ, which means measurement of Dmax and at 10.2 centimeters depth. So it's 5 points that you need to take. You also need to measure temperature and pressure, but really that's it. That's the whole protocol. So that's the quick and dirty version, but let's go into some details. So what I want to do is basically go through this equation and talk about each of these factors and share some of my thoughts on them. So NDW, of course, is the calibration factor for the ion chamber, and it relates our signal to dose. And it's provided by the ADCL. And 2 questions that come to my mind are, how does the ADCL generate this value, and what assumptions does it hinge on? And so we look at the first question, how does the ADCL generate this value? And the answer is by the replacement method. That's what it's called. So the normal equation is dose equals N times M. We can rearrange this so that we have a calibration factor equals dose over M. And if in that equation, if we know dose and we know M, we can get N. So the ADCL measures the dose rate of their cobalt beam at a specific point with a chamber that's traced to a primary standard, that is NIST, that is a calorimeter ultimately. So NIST will know what the dose is very accurately based on this primary standard, primary definition of dose. They'll ascribe a calibration factor to a chamber, and then that's replaced at an ADCL. The ADCL will put their chamber into the beam, figure out what the dose rate is at that point right there, and then they'll stick your chamber into the same point in the beam and get a calibration factor just by rearranging the equation, solving for N instead of solving for D. Okay, so what assumptions does this hinge on? Well, there's a couple of points to think about. If you change the amount of mass of gas in your chamber, you will change the signal. The dose rate hasn't changed, but the signal's changed. Therefore, this will affect N. Your calibration factor is going to vary. Therefore, when we specify an N, that has to be specified with a given mass of gas in the chamber, i.e. a specific temperature and pressure. And we do this by convention at STP, standard temperature and pressure, because that's easy. So the ADCL corrects their response, whatever they're measuring, to this temperature so that the NDW is reported for those conditions. A similar thing that it hinges on is that we have recombination in a beam. Not all ions are collected, and so the signal is underrepresented. This will also affect N. The more recombination we have, the lower the signal is, and that will manifest as a difference in the relationship between N and D, or sorry, between D and M, between the dose and the signal, i.e. it changes N. So N must have a defined ion collection percent. And we have defined as a field that it makes most sense to talk about full ion collection. So the ADCL corrects the response of their calibration to full ion collection. They do this through parameter A ion, which is just like P ion, except it's the inverse. But it gets the NDW to a point where it is defined for a specific ion collection percent, and that is 100%. So really we can take a step back now and look at NDW, and we know that N is clearly a function of beam quality, right? It says it right in the top, N in cobalt 60. It is a function of the dosimetric value that we're looking for. Here it's dose. You could also have an air kerma. And it's a function of your medium. It's in water. But it's actually more than that, right? They've sort of picked 3 parameters to describe N with, but there are more parameters that N is a function of. It's, as we just talked about, it's a function of temperature and pressure, and it's a function of ion collection. So the ADCL corrects the NDW to STP and full ion correction. And in order to use that NDW, you must also correct your measurements to the same conditions, to the same place. And that's done through application of PTP and Pion. Okay, next parameter in our equation, MRaw. This is, of course, just our raw signal. It's a measurement done with the axis of the chamber at 10 centimeters depth. And fun, interesting fact, farmer chambers are all approximately the same volume, which means they all have approximately the same NDW. I mean, it varies by 10% or so. But that means that you're going to get the same signal. It really doesn't matter what your chamber is. And even between different beam energies, there's not that much variation in your in the dose rate at 10 centimeters depth. So for a given farmer chamber in a calibration, you're going to get about 20 nanocoulombs per 100 mu. And that's a number you should expect to see. Anyway, just a fun fact. Okay, KQ is a little more interesting. So KQ, of course, our standard beam quality correction factor. This is determined with Monte Carlo, and it accounts for the difference in chamber response between the calibration conditions, where our N has been defined, and the measurement conditions, which are done in an arbitrary beam quality. And it's determined by measuring PDD10, or really PDD10X if we talk about the general case and we're worried about high energies. Okay, so when we get into KQ, we can't talk about that without talking about the effective point of measurement, So let me ask question 2 here. The effective point of measurement and the axis of the chamber are related how? And this question, like everything I'm going to talk about today, is for cylindrical chambers. So the effective point of measurement is 0.6 rCav for X-rays and 0.5 rCav for electrons downstream of the chamber axis, 0.6 rCav for X-ray and 0.5 rCav for electrons upstream of the chamber axis, 0.6 rCav for electrons, 0.5 rCav for X-rays downstream, or 0.6 rCav for electrons, 0.5 rCav for X-rays upstream.
Okay, thank you. This question is live, so go ahead and make sure to put in your answers now, since it's only going to be up for a minute, and then we're going to go ahead and review the answer. Also, I just want to make sure everyone's asking their questions in the chat. Make sure that you put something in there so that when we finish up the presentation, we can go ahead and review those answers. Looks like a lot of people have weighed in on this question, Stephen. I think we can go ahead and review it.
Fantastic. So good answer from everybody. Yes, the effective point is upstream from the chamber axis by 0.6 rCav for X-rays, 0.5 rCav for electrons. It's not a hard number that it's 0.6. Actually, a lot of them are 0.5, 0.4 for photons, but that's the number used in the protocol. So practically, when we're implementing this protocol, we determine KQ by measuring the dose at Dmax and at 10 plus 0.6 rCav, 10.2. When the answer isn't written out like that, I always pause a minute to think, okay, do I need to measure at 9.8, or do I need to put the axis of my chamber at 9.8 to measure 10, or do I put the axis of my chamber at 10.2 to measure at 10? And so which way to think is an important, or which way to shift is an important concept to know. And when I approach this, I always think, okay, well, our medium is water and our chamber is low density air. We have minimal interactions in the air in the active volume. This is the whole underlying assumption of cavity theory, Bragg-Gray, Spencer-Attucks cavity theory, is that we don't have interactions in this medium. The electrons are just passing through. So really all the signal is coming from the water. And because the radiation is forward peak, that means that the signal is coming from upstream and there's nothing happening in the chamber, which means that the signal is really an upstream phenomenon. We're measuring higher than the center of the chamber. This means that the effective point of measurement is upstream from the chamber axis. And this means that if we want to do an effective point of measurement at a nominal depth, we have to move the chamber axis downstream. So we're going to measure at 10.2 centimeters to make a measurement at 10. It may be a slightly different depth if you are not using a farmer chamber, one with that diameter, but if it's something with that diameter, then it's 10.2. Okay, so in reality, we're going to measure PDD 10x to remove the contaminating electrons. And this is relevant for beams that are 10 MV and above. If it's below 10 MV, there's no relevant contaminating electrons. So the recommended path in TG-51 is to use lead foil. And the idea here is that you're going to replace an unknown electron contamination, whatever's coming out of your accelerator head, with a known electron contamination, that which comes off a lead sheet. And this contamination, this known contamination from the lead sheet, has then been rolled into these KQ calculations. So we're basically forcing it into a known scenario. And there's an equation that will relate the PDD-10 in lead or with lead to PDD-10X, pure X-ray signal. And this depends on your lead placement. Unless you've got an Electa, you can really only do it at the 30 centimeters from the water surface. The Linac head doesn't have clearance for the 50 centimeter point, but that's fine. As a practical step, certainly at IROC, whenever we're doing calibrations, we skip the lead foil and use the average solution. Or this is the secondary equation, which is based on the average solution to the lead foil problem, or the lead foil application. And so that's I think, a simpler application that really works pretty much just as well. But you've got two different paths to remove the effect of the unknown effect of the contamination in electrons. Okay, so we call KQ a beam quality correction, but it's not just about energy dependence of the ion chamber. This is not just a ratio of stopping powers or some simple energy dependence. There's a lot of things that are going into the KQ calculation, right? As we talked about, it accounts for electron contamination from lead. It accounts for wall perturbations. It even accounts for the effective point of measurement. The dose is determined at the axis of the chamber in the Monte Carlo simulations. So this is why our chamber is placed at 10 centimeters and not 10.2, because all of these corrections are solved for with the Monte Carlo solution that determines what KQ is for these chambers. So there's a lot of stuff that gets rolled into KQ, and it's sort of a bit of a catch-all correction. Okay. So now we can talk about the next one, Pion. Of course, Pion accounts for recombination during charge collection. And it is going to correct us to full ion collection, which is the condition needed for N to be valid. Let's jump into question 3. Which value of Pion is necessarily not correct? I.e., which of these values is wrong? Which of these values, if you measured from Pion, should you flag?
Okay, great. So this question is up in the polls. Go ahead and answer it now while you can. And also, if you have any questions for Stephen specifically about the webinar, you can go ahead and ask those in the Q&A chat window. All right, wow, looks like there's a big split here with this question. Maybe this one's a little bit trickier. I think we can go ahead and review the answer.
Excellent. So everybody thought that 1.002 was totally reasonable. And the question is, what's worse, farther away or less than 1? And if you have a high energy FFF beam or electron beams, in fact, you can get pions that are in the order of 1.5 to 2%. So 1.018 is not unreasonable. The point to remember is Pion is correcting us up to our full ion collection. So Pion always has to be adding signal. It's always correcting for loss, i.e. it has to be greater than 1. So 0.997 is a nonsensical answer because that would mean we'd collected more signal than had been generated. I think we have one question that I will just take right now, which is using the average solution, the equation for FFF beams. Let me go back 1 second here. This second option of using the average equation is not currently endorsed by the in the addendum, the TG-51 addendum for 51 addendum for FFF beams. So for FFF beams at present, it's still the recommendation is to use the lead. Okay, so we'll go back to Pion. We know it has to be greater than 1 because we have to scale up our answer. And the reality is that it's a pretty stable number. It varies slightly with the type of chamber you have, but if you're measuring a 6x beam, your Pion is going to be 1.003 plus or minus 0.001. If you're measuring an 18x beam, it's going to be 1.006 plus or minus 0.002 or so. For electrons, it's higher. We have a higher dose per pulse, so it's going to be higher. But again, it's stable across for electrons, it's stable across energies. But it's a consistent number between different linacs. You're going to get about the same number. So there are two things that are of interest to think about with Pion. And one is how it increases with dose rate, or what it increases with dose rate. And two, it's calculated with the 2 voltage technique. Right? And so this equation is straight out of TG-51. Everybody should know it. This is for pulsed beams. I'm not going to talk about continuous beams right now. But this is the formalism we use for calculating the... This is the equation here we use for calculating Pion. But what's going on into this equation? Where does it come from? What are the underlying assumptions, and can we run into trouble with that? And of course, the answer is yes. So first, increase with dose rate. Let me answer this through asking a question. What happens to Pion if you change the rep rate from 100 mu per minute to 600 mu per minute? It increases, it decreases, or it stays the same?
Okay, great. So this question is live. You can go ahead and answer it in the polls section. And
Okay, it looks like we've sort of settled in here. A lot of people like it increases, and that is, well, that is in the right direction in that if you increase your dose rate, you're going to have more recombination, and therefore you're going to have a bigger correction to get you to full charge collection. I'm not going to call this a trick question, but this is an important medical physics concept. If you change the rep rate on your LINAC from 100 MU per minute to 600 MU per minute, you change the average dose rate. But how do LINACs change their rep rate? They do it by pulse dropping, both variant and elective. They might do a little bit of pulse shaping, but it's mostly pulse dropping. So if you change it from 100 MU per minute to 600 MU per minute, basically you're allowing all the pulses to go through. You're not changing what the pulse looks like. So what that means is that the instantaneous dose rate, the dose rate in that microsecond, is unchanged. And the detector, an ion chamber, responds on the time frame of about a microsecond. So the ion chamber does not see a difference between 100 MU per minute and 600 MU per minute. It sees the exact same dose rate. And so this is an important point because this is an error that's very common in the field, that you do not change, if you have a detector, you do not change the dose rate that it sees by changing the rep rate. So in fact, your Pion is going to stay the same. All right. But in general, if you do increase the dose rate, for example, by moving your ion chamber closer to the LINAC, that's a way to change dose rate. That will affect your recombination. Okay, so let's talk a little bit more about this 2-voltage technique, where it comes from, and what goes wrong. In TG-51, it does say it should be less than 1.05. That's part of what's going on here, is that you're looking for big issues, but that's not, it turns out that's really not sufficient, the guidance in TG-51 where it says be less than 1.05, because you have bigger problems, or you can have bigger problems. The equation that TG-51 uses for Pion is the solution to this general question of an assumed linear relationship between 1 over V and 1 over Q. So if you actually plot, which is an example of which is done here, 1 over Q and 1 over V, then you get, this is done for 3 different chambers and for 2 different energies for each chamber. So these are 6 different plots. So if you do Pion, you make this measurement at 2 points, and then you're going to do a linear extrapolation to 0, which is infinite voltage, which is the condition that gives you full recombination, or at least that's the assumption here. So you get full recombination when you have an infinite voltage. So we're going to take a measurement at 2 different voltages and extrapolate. And we're going to extrapolate assuming that it's a 1 over V, that is linear in the 1 over V, 1 over Q space. Now, if the underlying relationship actually is linear, right? So in this case here, in this data, you can see that it is linear. The data points form a nice line. You can connect a straight line through them. If the underlying relationship is linear, this is great. You put 2 points on the line, you can extrapolate that just fine. If the data is not fundamentally linear, if the behavior of the chamber is not fundamentally linear, then when you put 2 points on that line and you do a linear extrapolation, you miss the behavior of the chamber, because the behavior of the chamber is not linear. We just said that. So you are going to get a different answer when you extrapolate to this infinite voltage. You're going to get a different answer than what the chamber is actually doing, because you've undersampled the actual response of the chamber. And what this means is you're going to get the wrong Pion. you solve the equation numerically, it's fine. But conceptually, in terms of what the chamber is actually doing, it is wrong. And this actually has been a real problem. There was an interoperative beam that had used with a specific type of chamber, and I don't know what chamber it was exactly, but it did not have a linear response with between 1 over Q and 1 over V. And when the physicists did a simple 2-point or 2-voltage technique and did a linear extrapolation, they were off by something like 10 or 15%. And that led directly into an error in the calibration and led directly to the mistreatment of patients. So we can't always assume that linear relationships hold. They usually do. For a standard CRM LINAC, for a nice, well-vetted farmer chamber, this is very linear. It's nice and clean. But if you have a new beam, if you have a new chamber, you really need to test the recombination at multiple voltages to ensure this linearity between 1 over V and 1 over Q. And then once you know it's linear, once you know that the chamber behaves properly, then the 2-voltage technique is all you need. Pressure and temperature. Approximately all thimble chambers are vented. You get unvented chambers in LINAC heads. The MU chambers are unvented. That way they don't have to monitor temperature and pressure. They just rely on the massive gas that's trapped within the chamber. Of course, an interesting aside, the gas inside that sealed chamber, as you ionize it, the oxygen will oxidize with the walls of the chamber, and you actually lose massive gas. That's why your MU chamber drifts for a new LINAC as it stabilizes, as it pulls out the oxygen. But for thimble chambers, for ion chambers that we're using, these are vented. They're open to the atmosphere. So as pressure increases or temperature decreases, more gas is present in your active volume. And more gas means more signal is generated, right? This is the same thing as the N. You're throwing off the relationship between signal and dose. And so we have to mitigate this variability by using a reference condition. And this reference condition has to match the reference condition defined for your calibration factor, for N. So this is STP. Whether that's 22 degrees is used in TG-51 in North American protocols, or 20 degrees for TRS-398. Doesn't matter, but everybody has to point to the same spot. You got to point your reading back to the calibration conditions, back to how your N was defined. P electrometer is the next factor in here. Again, pretty straightforward here. This is calibration factor for your electrometer, and it relates charge or current, if you're doing it that way, to the reading of the electrometer. And again, this is generated by the ADCL. A known charge is applied to the electrometer, and the ratio of reading to value is determined by the ADCL. This is done over a range of charges to ensure this relationship is consistent over a range of readings, which it overwhelmingly is. There are very, very few cases where there are problems with that. For modern electrometers, P electrometer is very close to unity, right? We get weirded out if we see something that's bigger than 1.001 or less than 0.999. In the olden days, this calibration factor could be anything. It could be 8.3 or 2.7, all over the place. It doesn't really matter what it is. It's just relating what the reading is to how much charge has been collected. Okay, Peoplearity. This is the next term here that we're going to talk about. This, of course, corrects for different collection rates with different polarity. And the short answer is this value is 1 within measurement uncertainty. I mean, for low energy electron beams, 6E, not going down to 4, and I'm sticking with a cylindrical chamber. I've seen readings maybe as far off as 0.998, but it's really, really just 1. So, you know, it's a very small thing to worry about. Okay, next fun thing. We've made our measurement, we've done our calibration at 10 centimeters depth. Now we want to apply our PDD correction to go from 10 centimeters depth up to D max, right, where we're going to specify the nominal machine output. Sounds easy. And the big challenge and an interesting discussion comes up in terms of which PDD, because there are actually 2 PDDs in play here. We have a measured PDD, but we also have a TPS modeled or calculated PDD. And it's interesting because TG-51 says use the TPS, but we just finished measuring the PDD. We just did that for KQ. So why not just use that measured PDD that we've just taken and get a nice clean answer and not have to worry about the TPS calculation? And in theory, both of these approaches, whether you correct with measurement or whether you correct with the TPS PDD, you get the same answer, because those two values will be the exact same number. In reality, those two numbers are not the exact same number. And it's not uncommon to see 1%, even more than a percent difference between a measured and modeled PDD. So what's the difference between these two? Where does that one, maybe as much as 2%, but probably something in the 1% uncertainty range, where does that manifest? And the answer is, depending on whether we use the measured or the TPS PDD, determines where the dose is most accurate and where we've allowed that error to manifest. So let's go through these two scenarios. Let's just consider a 2% difference in PDD-10 between measurement and the TPS. If we use the measurement-based PDD-10 to correct, so we've just measured it for KQ, we use that PDD to correct it. The output that we measured at 10 centimeters depth is mapped directly to the output at Dmax, and that output is accurate there. However, when we then take that machine and calculate a dose with the treatment planning system, the error in the beam model, this 2% error in our beam model, as an arbitrary number, this 2% error in our beam model is going to manifest as a 2% error in the dose at 10 centimeters depth. It'll be accurate at Dmax and off at depth. If we use the treatment planning system, PDD-10, to correct, then our output is not correctly defined, right? We know what the measurement is, and we're correcting by a different number. So our actual measured output at Dmax is going to be different than the true machine output at Dmax. So this will be in error by our 2% at Dmax. But when we calculate the dose of the TPS, that error will be corrected by the time we get down to 10 centimeters depth. So the question is one of where are we going to be accurate? If we correct with the measurement, we're accurate at Dmax. If we correct with the clinical PDD, the TPS value, then we're accurate at 10 centimeters depth. And the consensus is that it's more important to be accurate at depth than at Dmax. Therefore, you correct the PDD using the TPS value, the clinical PDD. Okay, so that's covered a lot of stuff for photons. We'll spend a few minutes talking about electrons and a couple of things that are different. In general, electrons are very similar to photons, a lot of the same parameters. Instead of KQ, there's this K prime R50 KE cal. Instead of this gradient issue being rolled into KQ, we have an explicit handling of P gradient. And we're making measurements at DREF instead of at 10 centimeters depth, which means two things. One, we need to correct for PDD at DREF instead of PDD-10 to get our output at Dmax. And we actually are going to need to worry about stocking power ratios. So we'll talk about these things here for electrons. Again, cylindrical chamber for the most part. K prime R50 KE cal, tabulated values, much like KQ for photons. One of the big differences is that the gradient correction is not included with electrons where it is with photons. Again, this is so it's rolled into KQ, but here for electrons, it's pulled out as separately as P gradient. The one thing that I want to highlight is that unfortunately, some of the values of KE cal in TG-51 are not correct for parallel plate chambers. I don't know why this wasn't more publicly, why the public was made more aware of this, but some of the TG-51 values are up to 2% off from actual KE cals for those chambers. So if you're using a parallel plate chamber and you're using a KE cal, be careful, use your own cross calibration, or use a cylindrical chamber and avoid the issue. Again, you get into trouble, like below 6E is trouble, but 6E and above, cylindrical chambers work pretty well. Okay, P gradient. is the ratio of the measured signal at DREF plus 0.5 RCAV. So again, we're going to shift the chamber down so that our effective point of measurement is at our reference depth, divided by the signal at the reference depth. So what is this value, and do you need to measure it? And I'm going to harp on some of these electron things because it turns out, as we'll get into, these are actually where there are a lot of mistakes are made in these parameters. People get the wrong values. So just be aware of this. Understand what is going on and understand what the value should be so that you can know the wrong answer when you see it. So what is the value? What is P gradient? It changes with energy. Okay, if energy is less than 12 E, P gradient is greater than 1. For your energy at 12 E, your P gradient is going to be about 1. And for your energies above 12 MeV, P gradient is going to be less than 1. So you should see, if you're measuring P gradient, you should see the values transition through 1. And the reason for this is because for low energy electrons, DREF is at Dmax. And this places the effective point of measurement upstream in the buildup region where the dose is actually lower. So you get a ratio of readings that's greater than 1. I'll show this in a figure in just a second. At higher electron energies, DREF is downstream from Dmax. And so the effective point of measurement being upstream means that it's a higher value. And so the ratio of readings is less than 1. So if you get something different than this, double check your work, because I see this a lot. So let's go through this just to try to make this point a little more clear. Here is a 6E electron curve. And if we zoom in, we can see the physical depth here. So here is DREF, and here's DREF plus 0.5 RCAV. And the effective point is actually upstream of that. So if we take our measurement at DREF plus 0.5, that's this point here, and the reading is going to be high, a maximum, and MRaw at DREF is actually going to be less than that. So we're going to have a value greater than 1. Putting our chamber here actually gives us a higher reading than the chamber here because the effective point of measurements are here and here. So P gradient is going to be greater than 1. In contrast, if we take a high energy electron beam, DREF is downstream from Dmax. So again, we have DREF is here and DREF plus 0.5 RCAV. Our DREF plus 0.5 RCAV effectively is up here, and our DREF effective is up here. So our reading at DREF plus 0.5 RCAV is smaller than the reading at DREF. Okay, so in this case, the ratio is less than 1. So you should see this transition for P gradient as you move up your energies. Your other approach is we can ask the question, do you need to measure it? No, okay, so nominally to solve for TG-51, we're going to set the chamber axis to DREF. And then we get the equation dose equals M at DREF times a bunch of factors, N's, P's, yada, 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 times our P gradient. And our P gradient is M at DREF plus 0.5 RCAV over M at DREF. And if we look at this equation, it's not too hard to strike those two out. And it turns out that if we measure M at DREF plus 0.5 RCAV, so we align the chamber to the effective point of measurement instead of putting the axis of the chamber at DREF, you put the axis of the chamber at DREF plus 0.5 RCAV, and you measure with the effective point of measurement instead of the axis of the chamber, then P gradient is implicitly included in your calculation of the output. Now, the only thing to remember, of course, is if you make your calibration measurement at DREF plus 0.5 RCAV, that's also where you need to measure Pion and P-polarity. You need to do your polarity changing and bias changing at that same point. Don't measure half voltage and opposite voltage at DREF and measure your calibration output at DREF plus 0.5 RCAV, of course. You got to keep that all at the same measurement point. But then you can do everything at this point and you save yourself a step. Okay, one more thing for electrons, PDD at DREF. What should this be? What should this number be? And again, this is a case where I see a lot of issues come up. So I'm going to emphasize these. If you are at 12E or below, DREF is Dmax. Your PDD at DREF should be 1. By 16E, this is at about 99%. 18E, this is about 98%. 20E, this is 95.5%. you don't get these values, you better go back and double check. I've audited a lot of places where their PDD at DREF for a 20E beam, they had in at 99%, and that's not right. PDD at DREF should be down in the 95 to 96% range for a 20E beam. So one step, one complication in this PDD at DREF that everybody needs to be aware of is a very popular board question. For photons with depth, right? For photons, we didn't worry about it. We measured our signal at Dmax, we measured our signal at 10.2, and we took that as our PDD. And for photons, you can do that because what we're measuring is ionization, and what we're trying to infer is depth, is dose. But for photons, those are one-to-one correspondence, or at least it doesn't change. When the photon beam goes through a medium, it just attenuates. It doesn't change energy dramatically, which means that the secondary electrons don't change energy dramatically. I mean, it only changes energy because you've got extra scatter. But your primary energy is very much the same, which means your secondary electron spectrum is much the same. Stopping powers don't change. So your depth, dose, and depth ionization occur. Depth, dose, and depth ionization values are the same. So measuring the PDD is simple because we can just take it as the PDI. For electrons, the spectrum and therefore the stopping powers change with depth. The average electrons are slower, deeper in depth. So the relationship between ionization and dose changes with depth. And of course, as we know from taking a measurement with an ion chamber, this doesn't give us PDD, it gives us PDI. And we have to convert to PDD using the changing stopping power ratio to apply a PDD at DREF correction. And if you don't convert to PDD, for high energy electron beams in particular, you can get a 3 to 5% error in the PDD at DREF if you use your percent depth ionization curve instead of your percent depth dose curve. So it's important to make that to do that extra step. And most of the software will do that for you, converting your ionization to dose. But that's what's going on with it. And that's why you need to do it. Okay, so let's change gears a little bit. I think we've hit all of the parameters and what's sort of driving them. Where do we see problems or obstacles in beam calibration? I'm going to highlight some of the things from this paper that was a joint effort by a whole bunch of different QA offices that looked at where do calibrations go wrong. And there are some interesting findings and some trends. And on the other hand, it does get a little bit sad because a lot of the issues are almost anecdotal. There are so many different things that can go wrong in different ways that it can not work out, that really the best thing to do is be very careful. So electrons in general are more prone to errors than photons. There's a few more steps. It's a little more complicated with this PDD versus PDI. It's different between different energies. So you have a different DREF value. So it's not as consistent as photons, and so we see more errors than with photons. High energy electron beams in particular are very error prone. This is where we see many more errors than with photons or with lower energy electrons. But the simple answer is that all beams can have errors, and there's a lot of different causes. And we tried to break it out by what caused these. This was for a set of confirmed calibration errors. Where did those come from? What was sort of the root cause analysis of these calibration errors? And there was a long list of them. So here's, I'll just go through examples to highlight some of these. Errors in worksheets. This is this blue piece of the pie. So a sizable number of errors. So this is basically doing an incorrect calculation. So people set up their TG-51 worksheet and something goes wrong in that. And I've seen everything where a cell is multiplied twice, or a cell that should be multiplied in isn't multiplied in. Or I've seen things where somebody sets up a 6x spreadsheet and copies that over to a 10x worksheet, and the value for KQ is hard-coded and copies over. So it doesn't update with the new KQ. So there's lots of mistakes that happen because people implement their worksheets incorrectly. There have been problems with equipment, be that broken equipment or incorrect equipment. As I alluded to, wrong K-ecal in TG-51. That certainly is hard to fault the physicist for, but it's nevertheless a problem in the calibration. There was a very recent case where there was a bad triax. It was actually the B and C connection that connected the main triax line to the electrometer. And the institution got very consistent results. Their output checks, their independent output checks came back 8% different. They changed ion chambers, they changed electrometers. They kept getting the same answer and it kept being stable. They finally changed the cable out, and that made a systematic 8% difference in the output. So it can be little things, and I mean, it's a terrifying manifestation that you have a systematic error that is so consistent and so stable and of an 8% magnitude. But this is some of the stuff that's been observed. So this is equipment errors here, this orange piece of the pie. This gray piece of the pie is following the protocol. Basically, did you do all the steps of the protocol? And one that comes up a surprising number of times, surprisingly frequently, is a failure to apply a PDD at DREF correction for the electron beams. So again, you hit those high energy electron beams and your output goes off by 5%. Other errors. Errors in data entry have been seen. Typographical errors. There was a case where somebody had an electrometer and the electrometer factor was 1.001 and they typed 1.01 into their TG-51 spreadsheet. Errors in setup. Of course, these can manifest as well. And a classic one is a wrong SSD. So you set your water tank up, you're doing your photons, you don't have clearance to put your electron applicator in, so you lower your water tank down, you stick your electron applicator in, and you forget to raise your water tank back up. It happens. This green one is errors and corrections, and I've separated out errors and corrections and errors in the PDD correction. So errors and corrections, the wrong correction is determined. So this is common, surprisingly common with barometers. The wrong value is used. The barometer isn't properly calibrated. Temperature pressure correction is not correct. Or errors in looking up KQ. Right? The PDD-10X has been measured correctly, but then the transferring of that to either looking it up on the graphs in TG-51 or putting it into the analytic expression of the TG-51 addendum, the third order polynomial, is done incorrectly, and so you get the wrong KQ. There's this huge other separate piece of the pie that's left here for PDDs, which again just underscores some of the challenge in this particular factor, because we've already talked about this gray piece was failing to follow the protocol, and often that was failing to apply a PDD at DREF. But this whole other piece of the pie is using the wrong PDD at DREF. So people apply it, but they use 99% for a 20E beam. That's not the right value. Or they use PDI instead of PDD. Mistakes come in. So mistakes manifest in following the protocol, determining the correct values for the protocol, ancillary steps like setting things up. They show up all over the place. So just as some final thoughts, be careful out there. I will just say, make sure you get an independent check of your output and make sure that that's periodically done. And hopefully this will provide some insight into the calibration protocol, and that will reduce risk of errors as you move out into the community, or if you're already there, as you continue your practice. And this is WePass. Hopefully this will provide some helpful insight in understanding this protocol for the examination. And that is all I had, so we can turn to some questions.
Great, thank you so much, Stephen. We still have some questions coming in, so we'll just give folks a moment here. Great. So I'll go ahead and say the first one here. How large is the error associated with not using a lead foil for FFF beams?
I don't have a concrete number for that. It's not large, but it hasn't been sort of rigorously evaluated. It's actually something we're collecting data on at IROC right now. because we hope to do this because we don't like measuring with lead either. So when we go to an institution audit, we just want to stick our ion chamber in and move on with life. So I don't have a good answer for you. It's probably pretty low. But I would wait and see or test it yourself, right? I mean, this is the sort of thing on your machine. If you test it, I think there's a good justification for not doing it again, right? Do it with lead, do it without. And if you get the same answer, move on with life.
Okay, thank you. Is a cylindrical chamber preferable for electrons?
There's an upcoming report from AAPM, which will be a TG-51 addendum for electrons. And the expected report, or it is expected that that report is just going to say, use a cylindrical chamber.
Okay.
It is more, if you get down to the 4E range, things are messy. But the benefits so parallel plate chambers are a little more complicated, and it was hoped that the positioning would be more precise, and that would overcome the limitations of the cylindrical chamber. But it turns out that one cylindrical chambers really are pretty good, and the parallel plate chambers are just a little too messy. So it's just more headache. So the field's going to be better off just using cylindrical chambers.
Thank you for answering that question. Our next question is, can you please discuss why you make measurements at 10 cm depth and then calibrate at Dmax? Why not just measure at Dmax?
Particularly for the high energy beams, you've got a lot of electron contamination in there. So the protocol would have to be written up to separate out high energy versus low energy in different depths. You're also sort of in this plateauy region. If you're at 10 centimeters depth, it's a nice stable position. It's a nice clean place to make a measurement. I mean, could that have been 5 or 15? As far as I can figure, yes. But the Dmax is just not as clean an area as 10 centimeters.
Okay, great. Our next question is, what is the future of calibration protocols? Will there be a new international protocol like TRS-398 soon?
There is a TRS-398 update coming out. It's a few years off still, although I think most of it is done. It will, again, there isn't much difference between TRS-398 and TG-51 when you boil it all down. The TRS-398 protocol is broader, so it will include updates for orthovoltage, particle therapy, those sorts of applications. But at this point, really, and as I said, there is a TG-51 addendum coming for electrons that will do some practice changing, like, as I said, expecting there to be just recommendations on cylindrical chambers. And that's sort of what's in the works for that'll sort of be the next 5 years.
Thank you. Thank you for answering that question. Our next question is, please discuss the PRP correction factor for FFF proton beams and how it would be measured.
FFF proton beams?
Photon beams.
Okay. So the PRP correction and it comes up because we have a non-uniform dose distribution and we're trying to reflect dose at a point. So we have some volume averaging of our ion chamber. And if the dose is dropping off, we want to measure the dose sort of at the peak. If we have a peak distribution like an FFF beam, we want to know the dose at the peak, and we don't want to weigh in the dose as it's dropping off on the shoulders. So the PRP is a correction that just takes basically the loss of signal at the edges of the chamber where the dose is starting to drop off and corrects that back up so that we get the dose at the peak. And really a 1D correction is all you need here. So I would take a piece of film or something, your chamber's 2 centimeters long, just measure the dose over those 2 centimeters or over the length of your chamber, whatever that happens to be. And it's just a 1D integration. So how much does the signal, what's the average signal compared to the signal in the peak? Obviously, you're going to want to play with averaging and how much of a region of interest you take. But what's the average signal compared to the dose, or what's the average signal compared to the signal at the peak? And that's your PRP correction.
Thank you. Okay, as you mentioned, PDD differences between measured and TPS calculated values for photons. How about R50 values for electron measured or TPS calculated?
Good question. I would still use your clinical value. And for electrons, it's only messy because There are places that are still sort of using tabulated values and sort of measurement-driven systems. So ultimately, the more you can tie it into your treatment planning system, this is a good rule for everything. If you're doing any sort of QA, and so it's true for this calibration statement as well, but the more you can tie in your TPS, the more you've linked those two systems, because that's really a bit of a weak link in medical physics. We do very exquisite work on the LINAC, and we do very exquisite work on the TPS, and we don't do as good a job making sure that those things are matching. So take it from the TPS, or take it from whatever you're using your clinical value for, however you determine that clinically.
Thank you for answering that question. All right, we have a few more here. If our chamber is calibrated by an ADCL at negative 30 V, does it make sense to apply PPOL? I'm not sure if I'm reading that correctly.
So again, what the ADCL is going to do is give you an N that's at a specific set of conditions. And that should be the sort of the average representation of positive and negative. At an ADCL, it's a different beam. It has some slightly different characteristics. I mean, we could have this conversation about should we even be measuring Peoplearity? It makes some sense if you have a parallel plate chamber and a low energy electron beam, because you can have some scatter in of electrons. So you can actually get some Peoplearity at that point. But just because the ADCL is doing that, I wouldn't. In general, this is a small correction. It's hard to fight a lot of battles over it. But what you're getting from the ADCL should, in theory, be the average, the signal that would be appropriate for an average. So that's what you want to represent as well in your measurement. So that's why you want to take it. That's why you want to measure Peoplearity and make that correction.
Okay, great. We have another question related to that as well. I've always wondered about Peoplearity. Why would we ever change the polarity of the chamber during measurement?
And again, I think that's a fin, because is this something we should really be worrying about for cylindrical chambers? I'm not convinced that it's outside of measurement uncertainty. I think it's good to understand the chamber, how your chamber is behaving. Again, if you have a parallel plate chamber, this is something where you can start to see some effects come up, and it's good to understand what your chamber is doing. But practically speaking, this is a small factor, and you're not wrong to wonder if it's worth doing. That's sort of at the that's sort of up the TG members.
Okay, thank you. Our next question, how would a parallel plate ion chamber like PTW advanced Marcus would behave in a proton beam as it moves from the plateau region to the peak regarding the ion recombination?
So here we got to go back and think a little bit about our recombination, because there's two factors, right? For low LET radiation, almost all of the recombination occurs as particle tracks cross. Well, not as they cross, but as secondary electrons from two different tracks mingle. So this is a dose rate question for low LET radiation. If you get into high LET radiation, you start to get recombination along the track of the particle as well. It's sort of called initial recombination instead of this volumetric recombination. So when that starts to dominate, I'm not entirely sure, but you're going to start seeing more of an effect. So as you move in a proton beam, as you move into a higher LET region, your dose rate is going to stay about the same between the plateau and the peak, but your LET is going to go up. So you should see more initial recombination. So you should actually have a larger correction factor as you move up. Right, those are sort of the two factors that are going to go into this. How many tracks are crossing your chamber, and that's going to lead to more recombination. And what's the LET? And the higher the LET, the more recombination you're going to have. Those are the two sources. As either of those go up, your recombination is going to go up, so your correction factor is going to be bigger.
Okay, great. Thank you so much for answering that. Our next question, the virtual source position measurements. Which phantom should be used? Solid water or by using RFA? This is from Priyanka Agarwal.
Yeah. Let's see. So virtual source position measurement should start from isocenter as near as distance as possible. I would start from closer than isocenter, because you're going to get the further you are away, the smaller your inverse square effect is. So the closer you are, the more pronounced the inverse square effect is going to be, which means you're going to be able to better solve the fit. The closer you are, of course, the more uncertain or the more sensitive you are to your positioning as well. So it's a bit of a balancing act. So I would certainly, my instinct says to start closer. I don't know if there are recommendations on that offhand, but I would certainly start closer and take advantage of that sensitivity without trying to get too close so that it's uncertain.
All right, thank you. Our next question, TG-51 requires Pion less than 1.05. Why is that the tolerance?
And this, as far as I understand it, is really just an attempt to keep this correction manageable. And this goes back to the classic argument of the smaller your correction is, the smaller the uncertainty in that correction should be. And so they say, well, let it be less than 1.05, because that way, if we have hopefully that way the correction will be reasonably accurate, the two voltage technique. And we know that this really isn't the driving problem here. The driving problem is, do we have nonlinearity in the 1 over V, 1 over Q space, where a 2 voltage solution is not even the right shape of the curve. But this speaks a lot to the keep uncertainties or keep correction factors small, so that small correction factors mean smaller uncertainties in general.
Okay, thank you. Our next question, why PDD10 and not TPR2010?
You could get a couple of people in a room who will argue this point until they're blue in the face. TRS-398 went with a TPR2010 formalism. TG-51 went with a PDD10 formalism. Either one is a description of the beam quality. The TPR2010, you're not working in the space, you're not qualifying the beam energy based on what's happening near Dmax, so you never have to worry about using lead, like a piece of lead foil, to correct for electrons. So it's a little cleaner in that. I'm not sure why they went with the PDD10 formalism to begin with, but certainly the evidence is that it works fine and that you can do this very accurately. Both of these protocols, the TPR2010 TRS-398 and PDD10 TG-51, are equivalently accurate, and I've never heard anybody say anything different. So either works.
Okay, great. Thanks so much for answering that one. Our next one, how much approximately does the lead foil correction change the final calibration for, say, an 18 MV beam? I assume less than 0.5%.
I guess the question is relative to what? Because if you're talking about relative to using the other equation, the average solution, then it's, I think TG-51 says in extreme cases, it could be 0.4% different. So if you're talking about lead foil versus using the equation, using the other equation to map PDD10 to PDD10X, then it's 0.1, 0.2%. And that's why, at IROC, we just skip the lead, because it's good within 0.1% vast majority of the times, and that's good enough. If you're talking open PDD versus PDD10X, that's going to be a very different value. And that's going to be a much different number. It doesn't manifest as that much of an error in your calibration, because that PDD value is then being converted into a KQ. So you're going to get an incorrect KQ. So you're going to get several percent difference in the PDD10X versus PDD10 open. That will correspond to probably a fraction, but maybe a large fraction of a percent error in KQ.
Okay, thank you so much for answering that one. Our next one, are you using the average solution for FFF beams also, or using lead?
And we talked about this one earlier, that for FFF beams right now, it hasn't been validated. I would test it out myself. We're doing this here at IROC to test it out. Hopefully we can get rid of lead.
All right. We might have gone over this one as well. Is the NIST measurement at 10 cm depth?
The NIST measurement is not, because all they're doing is defining dose at a point, and it doesn't matter what that point is. So an ADCL measurement isn't done at 10 centimeters depth either. It's usually done at sort of 5. But it can be done at whatever point because it's going to be a substitution method, right? You make a measurement of dose at a point, and then you stick your chamber of interest at that point. And you know the dose rate there, and so you get this relationship. And it doesn't matter where exactly that dose is, or where exactly that is in the water tank.
All right, great. Our next question, can you reiterate the dose rates considerations for FFF beams?
There is a big question. So for FFF beams, you're going to see there's two things to bear in mind. One, you have a genuine higher dose per pulse. So your dose rate, your instantaneous dose rate is higher. That means you're going to have more recombination, and that means you're going to have a bigger Pion. So you will have a larger correction. Instead of it being 1.003, it's like 1.013 for 6 FFF versus 6X. So it's a larger correction. That's what it should be. The other question that's come up and something to bear in mind is as you push that dose rate up, you want to make sure that your chamber behaves linearly in that 1 over Q versus 1 over V space so that you can use that 2 voltage technique and you can use the Pion equation. So there have been a lot of evaluations of different types of chambers in FFF beams. So far, everything looks good and behaves well. But if you have a new chamber type and you can't find it, that's a step you'd want to take for a new beam type like an FFF.
Okay, great. Thank you. Our next question. If our farmer chamber is calibrated at negative 300 V by the ADCL, should we omit P polarity?
I think we did that one.
Okay.
And basically said, no, you still need to do it because the ADCL is going to map everything back to uniform space and you need to be in that space as well. Okay,
our next question. For measuring Pion in a new chamber, many electrometers have only have a few possible voltages. How confident can we be that 1 over V to 1 over Q relationship is linear?
This is a really good question and actually a real problem in that MedPhys went this 2 voltage technique for so long that the vendors have started just giving you 2 voltages. When I did a set of experiments here at MD Anderson to look into this 1 over V versus 1 over Q, I had to dig through the basement to find one electrometer. Of the 30, 40 electrometers we have here, I could only find one that would allow me to set a range of voltages. And so that's sort of the path you have to take in order to do this measurement. You have to have an electrometer that can do different voltages.
All right. I think we're going to end the Q&A there since you've given us so much of your time. And we really appreciate you, Dr. Cry, for presenting this webinar. And thank you all for joining us for this free event hosted by WePast. So please be sure to join us for our next webinar, an introduction on MRI-based treatment planning, presented by Dr. Tong Wang on Wednesday, January 29th at 6 p.m. Eastern. And just keep in mind that this and other recorded webinars are always available to WePast subscribers 24 hours a day, 7 days a week. So if you want a review, go ahead and register through WePast.com to become a subscriber. And for up-to-date information about upcoming webinars, be sure to follow WePast on Facebook, Twitter, and LinkedIn. Thanks again, Dr. Cry, and I hope we'll see you soon.
Thank you.
Have a good day.
You too.